Okay, so here's a problem from China TST 2016. It says that we have any integer, any positive integer, we define a function. Then you want that this number is divisible by all positive integers a smaller than or equal to m with a odd. So first, how do we approach this? Well, notice that this is, constant for m constant. So what is it's actually asking is, this is divisible by the LCM of 1, 3, 5, ... And then I guess I'll write 2 times n over 2 ceiling and then minus 1. So it's divisible by this thing. We only need to prove this. Then you think LCMs are actually pretty bad. Like, how do we even get the hang of LCMs? So you start thinking, hey, can we change this LCM into, for example, we have p to the something is divisible by this product. And the answer is yes, we can do that. Well, how do we do that? So we take the p, for every prime, I'll write that down, for each prime p, take the maximal, I won't use k, because k is in the problem. I'll use s, such that p to the s is smaller than or equal to m. So we just need to show that p to the s divides this weird product over here. Next, let's characterize f of m a little. So basically what it's telling us is that k is v2 of m. And then we have the thing remaining when we divide m by all of its 2's. Then we take the 1 minus kth power. So it's kind of this function. Now, the next thing to observe is you can take vp of both sides. So then what happens? Well, we're trying to prove s smaller than or equal to vp of this. And obviously, vp of product is just sum of vp's. So we have this. Honestly, does this look kind of simplifiable to you? It does to me. So how do we simplify this? Well, obviously, this is 0 when m has nothing to do with p. So if m isn't a multiple of p, we can just ignore it. Let's rewrite it like this. So we have the sum of some divisors of p, but not too large. And then we just want vp of f of m. So that's actually asking for, we don't care about the 1 minus k over here. We just need, we don't care about the rest of t. So let's add in the 1 minus k later. Let's think about t. Well, dividing by 2 won't change vp because a is odd, so I forgot that we're assuming p is odd. So this, we don't care about this. This is only involved in the 1 minus k. So now let's look at t. Well, vp of t is just vp of m. What we're doing here is actually we're taking vp of I. Then we're multiplying by 1 minus k. K is v2 of I. This still looks simplifiable to me. So what do we do here? Well, you can see that this vp of I is kind of awkward. So the thing I think of is this. How do you calculate v2 of, say, 10 factorial? Well, first you would take the multiples of 2, which is 5. There are 5 of them. You would take the multiples of 2 squared. There are 2 of them. And then the multiples of 2 cubed. There are 1. There's 1. That's 8. But how does this work? Well, essentially, you're summing up. You're trying to find v2 of this. So you're summing up from I equals 1 to 10 of v2I. Then what you do here is you can change that to the sum of I equals the sum of, actually no, I'll just do it this way. So you'll write it as this. There are v2I ones. Again, an empty sum is defined as 0. Then what happens here is you take the first one. There are 5 terms. Like to write it like this, there are 10 over 2 floor terms that have the first one, that have at least one A1. There are 10 over 4 floor terms that have at least 2 ones, and so on. You'll see that this is actually an infinite sum, but all of the rest of the terms are 0, so I'll just delete them. Do you see how this is related with this? So the relation is that we can do the exact same to this guy over here. We're just summing up from I equals 1, not 0. 1 to, we may assume, infinity. And then we want p to the I. Actually, this summation is to s, just to make it clear. Then we want p to the I divides j. I'll use j. 1 smaller than or equal to j, smaller than or equal to m. Then you have a vp of I. Oh, you don't. And then you just have 1 minus v2 of I. Well, why are we... Oh, j. Why are we even caring how many p's are in j anyways? As far as v2 is concerned, we can just rewrite this as this. So basically what we're doing is we're dividing all of the valid j's by p to the I, and since that doesn't affect v2, we're still good. Now our aim is actually to calculate this thing, which is basically to calculate the j equals 1 to some integer. I'll use n of 1 minus v2j. And as far as I know, this is a pretty standard result, but I'll just look at it. So what happens is you realize the sum looks like 1, 0, 1, negative 1, 1, 0, 1, negative 2, 1, 0, 1, negative 1, 1, 0, 1, negative 3. And after a bit of experimenting, you see that the minimum of this is actually 1. Can we prove that? If we prove that, we're done, because there are s of these. So since the minimum is 1 for each, we have the answer s. How do we prove this? Supposedly it's a pretty standard result, but I'll just prove it here anyways. So, oops. I gotta do this. Hold on 1 second. Done. Now, what we're trying to prove is the sum from j equals 1 to n of 1 minus v2 of j is larger than or equal to 1. How do we prove this? Well, you can see from the sequence that the equality is only at 2 to the I. Hey, if we bring out this thing over here, somehow this calculation has quite a bit of relation to this problem. If we bring back our calculations of v2 10 fact, we see that we have the exact term appearing here. Basically, if n is 10, we see this appearing in this. Now let's just replace it by that. It's just n minus v2 of n factorial. Well, honestly, we don't like that. We want instead the sum of I equals 1 to, as far as we're concerned, infinity, n over 2 to the I floor. Why is this at least 1? Because this is equal to, well, it's actually larger than. Now here it needs a little of a argument why it's not equal, but obviously it's not equal, as we'll see later. N minus the sum of n over 2 to the I. So notice that I just removed the floor. And this turns out to be 0. But why is this larger than? Well, that's simply because when I is sufficiently large, this guy is not an integer. Therefore, it must be a decimal. Therefore, there is some loss in this step. And since this is an integer, obviously, it must be larger than or equal to 0. So we solve this problem.